Hi, everyone. Welcome back to the second part of today's workshop. We will have two more interesting talks. The first talk is by Cathy Wu from MIT. Cathy?
Thank you, Wei-Hong, for the introduction. So I'm a relatively new faculty at MIT. I'm in LIDS, which is the Laboratory for Information and Decision Systems, the Department of Civil and Environmental Engineering, as well as IDSS, which is the Institute for Data Systems and Society. And I'll be really excited to share some of the journey that we've had over the last few years, sort of trying to see if this, what I think to be a really interesting problem domain, has anything to do with reinforcement learning. And what we've sort of found is that it's actually pretty hard to find a real world application that is a good fit for reinforcement learning, which I think is a good reason for a lot more intellectual work, a lot more research. So what I'm going to try to do in this talk is actually try to convince you that there is a set of really interesting problems that requires a lot more attention, and hopefully this will spur a lot of discussion along the theoretical lines. This talk itself is not too theoretically focused, so there will be a few connections. So the motivating question that has sort of kept me up at night over the last few years is, how can we quantify the impact of technology on societal systems? So at first, this may not seem like it has too much to do with RL, but just to say a little bit more about the motivation, the pace of change and the pace at which we're introducing technology into society is increasing. It has a lot to do with how quickly AI is developing as well, the extent to which we've been introducing automation into our systems over the last several decades. And as a result, the complexity of our systems is also increasing. And it's increasingly difficult for us to work with our existing tools. So let me give an example here. So one example of a societal system is a city. So this is a slice of society. And we've been adding a lot to it. So just in the last decade, roughly speaking, we've added smartphones, we've added high-speed cellular networks, we've added navigation and routing apps, we've added mobility on demand services like Uber, we've added advanced driver assistance systems like Tesla, and then upcoming in the future we have autonomous vehicles, drones, and we can expect a lot more in terms of technology, in terms of connectivity, automation, AI being introduced into these systems. And this combination has some impacts on public safety and health, on economic well-being, on sustainability, on resilience, equity, fairness, a lot more criteria that we really care about. But actually, that's not how we think about these systems when we design technology and introduce them. We actually just build it and then add it to the system. We don't really think about the impacts, except for instance, the bottom line of a company and whether or not it's financially sustainable to even build the product. So if we squint a little bit, I will argue that the city here, you can view as an environment. It is a dynamical system that has internal transitions and has some sort of dynamical evolution over time. Again, if you keep squinting, these pieces of technology, business models, and so on, you can view as an agent that's interacting with this environment. And then we can also view these impacts as a sort of reward or an objective that one could potentially optimize for. And then we might view policy evaluations. So for instance, we might take some of these agents, maybe they're not training, maybe a company has built them, but we would like to know the impact of these policies on the system, on the environment, which is the city. And so we can actually try to evaluate the policy on this reward. And if we take it a step further, we might consider policy learning. So some of these are not fixed in stone. Uber is a set of algorithms, and those algorithms can be updated. And as those algorithms are improved, can we also improve the impact of these policies or this type of technology on the system? Okay, so this is very high level and abstract. Let me give you one concrete example that I really like that inspires a lot of my work, that I think will helps to shed some light into why one might want to do this. So I've been really excited about self-driving cars for the last decade, and it's in part because of a lot of the promise it brings in terms of reducing traffic accidents and um, it being good for the environment, providing access to those who are unable to drive, and so on. And one of the really compelling aspects of self-driving cars is that it can potentially save a lot of fuel and help reduce our greenhouse gas emissions over time. And so if we actually look at that in more detail, however, transportation currently accounts for about a third of energy consumption in the US. And then if we project this forward in time to some arbitrary date, which is when some experts believe that we can have fully automated systems, there's actually a really large degree of uncertainty. So we could decrease our energy consumption by 40%, but very similar works. If you twiddle the numbers a little bit, then we might actually see a doubling of energy consumption. So we might build this system and introduce it into our cities, and we don't actually know which way we're headed. And so just for the curious, there are a lot of factors that go into whether or not we're sort of improving or worsening our energy consumption. So platooning and eco-driving, these are sort of smart driving strategies that are enabled by autonomous vehicles that can really reduce our energy consumption. But there are a lot of different factors. These are very complex, and the sort of culprit is that with self-driving cars, a lot more people will end up driving because it is a lot less taxing on our own time. Okay, but what I wanted to dig into here is that not only is this uncertain, this period, where we're headed, what's also uncertain is what's in between. And I'm not suggesting that we cast this entire thing as a reinforcement learning problem. That is quite far from where we are as a field, maybe one day. But I believe that reinforcement learning can actually help us understand this transition in the middle, the points in between, to help us make decisions as to how we can steer, how we can inform potentially policymakers to help steer us in the right direction as opposed to the wrong direction. So we don't know what this looks like. We don't know if we could have a straight shot to a more sustainable situation. We don't know if it's somewhat nonlinear. We don't know if there's some nonlinearities. Okay, so the first thing that you might ask when applying reinforcement learning to a non-standard problem, so we're not talking about grid world, we're not talking about MuJoCo, the question might be, where do you get the data? Reinforcement learning is very, very data hungry, and simulation is sort of the lifeblood of a lot of our work in recent years. So the good news, I would say, is that we actually build our cities based on simulation. There's a very healthy ecosystem of commercial and open source urban simulators. These will take some real world snapshot and model it exactly to the extent that we have data, and can do this at very large scales as well. So this is sort of the good news, in the sense that we don't necessarily have a ton of data, but we do have enough data that we can inform simulations and models well enough that experts actually are willing to trust the results of these simulators when designing cities, when designing where new roads should go, how roads should be lengthened, where hospitals should be built, and how that affects the shape of the city and whatnot. So that's sort of the good news. Now, it's not then just straightforward how you can apply reinforcement learning to this problem. We still have to very carefully define the problem. So it's somewhat tricky to sort of project down a very complex problem space into 2 dimensions, but here's my attempt, and it'll also serve as an outline for the key points of this talk. So I will give 2 axes of difficulty, so to say. So the first I will say is along this degree of autonomy. So you can imagine this to be no autonomous vehicles and all autonomous vehicles. There is a long heritage, so we're not approaching this from a perspective where this problem has never been attempted before, and reinforcement learning is the first thing that we're trying. There is a long heritage from control theory and stochastic systems. Um, I'm jumping ahead of myself. So just to make it a little bit concrete, we're going to start out with a very, very simple system, and I'll give another axis of difficulty later on. So this very simple system you might consider to be a one road, whether it's a circle or not, that's flexible, but there are very, very few vehicles on it, 1 to 20. This is not, so this is still a very toy system. This is not something that you would ever see in real life, but it is a model of, it is a simplification of something that you might see in real life. And so you might have such a scenario with no autonomous vehicles, and then you might have a scenario with all autonomous vehicles. Okay, and then now drawing from this long heritage from control theory, we actually have a lot of tools to analyze fairly simple systems with fairly low concentration of autonomy, as well as from stochastic systems on the other end. So we actually have, and I guess I want to make a comment that what makes these systems feasible up to this point is that it's not that we're solving the problem in full, but that we're actually willing to assume or constrain the problem such that we have low uncertainty and rewards. So for instance, we might consider a simple system, we might consider a PID controller, and we might consider that we're going to control one vehicle, and we're going to just be concerned with the velocity of that vehicle, and we want that vehicle to go fast. So we're constraining the reward to just that one vehicle, whereas if we were to say we care about the whole system, then there's a lot of uncertainty in the reward. Okay, so that's sort of one point that I'd like to make on the low autonomy end. And then the high autonomy end draws a lot from stochastic systems, from queuing theory. So for example, polling systems. And yeah, I should note, I did not add citations to this slide, but this slide is representing decades of work. So if anyone's interested, I'm happy to send you references. So on the far other end, one might think that as we increase the degree of autonomy, well, we have more and more control variables, and then we have a curse of dimensionality. And yes, that is true. But at the same time, we have a lot, at the very extreme end, we have low uncertainty in transitions because almost the whole system is determined. The credit assignment problem becomes very easy when every action you take produces a result that you can characterize very well, and then you can actually resolve the uncertainty quite well. All right, so that's sort of the first question. In between here, we actually have high uncertainty in both rewards and the transitions, and we can actually consider the scenarios on both ends where we have high uncertainty in rewards as well. So here we sort of have a chasm where we don't necessarily have good techniques to assess these systems. So then the question is, does RL fit in here? RL is designed for this high uncertainty environment. We know we have simulators, so we have infinite data, although we still don't want to use infinite data. The other axis of uncertainty is along the scope of the environment. And you can roughly think of this in terms of the number of vehicles of the road network. And there are a lot of other dimensions, but this is sufficient for the purposes of this talk. And so we might consider something like a downtown of a city with 500,000 vehicles, 10,000 roads, and so on. And there are, again, techniques drawing from control theory and stochastic systems that allows us to assess sort of around the edges of this problem space. But here we do really suffer from the curse of dimensionality as the system is increase in size. So I would like to point out here that there are a couple notions of curses of dimensionality, and the first of which is what we're used to, which is that as a state and action space grows, we suffer from that curse. But there's a more subtle one, which is that as the scope of the environment grows, there are actually combinatorially many more environments that we're interested in. So you can think about the possible number of road network configurations. If you have 1 road versus 5 roads versus 10,000 roads, the number of ways to redraw a road network explodes as well. So not only do we have environments that are harder to solve because the state action space is larger, but there are exponentially more environments as well. Okay, so I'll get to this later. So then that's sort of the second challenge. So what we're going to do is we're going to start out very simple, and we do want to see, is RL suitable for this problem? So just to be concrete, our agent is the autonomous vehicles, and our environment is everything else in the system. We're going to be controlling where our action space is the vehicle accelerations, for instance. We're trying to learn a policy to maximize some reward, and we're concerned with the average reward, for instance, of the entire system and not the constrained reward for a single vehicle. We're going to maximize the cumulative reward over time, and we're going to optimize for some parameters of some policy, which is a deep neural network. We're going to employ policy gradient methods since we're dealing with continuous control problems. And like I've said, we've seen a lot of success in very difficult benchmark tasks, but we're very curious if now this set of methodology can actually give us some insights for some societal systems that we may be interested in. So if we take a look at this simplest case, what we can actually do is let's actually consider some characteristics that we can draw from control theory. So let's consider in the x-axis vehicle density, so different numbers of vehicles on a road, and on the y-axis the average velocity of the system. And we can actually plot the upper and lower bounds of the system from equilibrium analysis. And so I have a video for the lower bound. So this is what you do without any control. So the vehicles sort of start out evenly spaced, but traffic jams like quickly form. So you can actually see this backwards propagating wave. It's very common in traffic systems. The upper bound is something that we can numerically compute we can compute this line, but we can't necessarily synthesize a controller that will achieve this line. So one of our curiosities is when we employ deep reinforcement learning to try to control this system by controlling a fraction of these vehicles, where do we fall in between these bounds? So what there's some recent work that hand designs a proportional integral controller that sort of falls in between here when one vehicle out of the system is controlled, one vehicle is observed. We do the same, but now we're employing policy gradient methods. So it's not hand designed. We're using an MLP controller, and I'll just sort of play the result of the learned controller. So the learned policy is currently off so that we can actually see these backwards propagating waves form again. And then at this line right here, which is now the automated vehicle controller is switched on, you'll see it takes on a sort of different driving profile, and it sort of opened up a gap and it quickly closed it. And when it closed the gap, there's the backwards propagating waves are gone. And actually this resulted in a 50% increase in the speed of the system. So when we actually take a step back and we do this across the vehicle densities, we actually see that the learned controller can closely match this optimal velocity curve. So sort of a question on the theoretical side that we don't have the answer to is, when can control theory and reinforcement learning actually be a really happy marriage here, where potentially control theory can actually provide these optimal velocity curves, the outcome, but not synthesize the controller, potentially in what is the class of problems for which you can have this nice pairing of using control theory to actually verify the optimality of a learned controller. Because it is often the case that in deep RL, you don't know if your controller is optimal. But in this case, we do by borrowing from control systems. Another thing to note here is that which will segue into the next part of this talk, is that the white regime is actually where we trained, and then in the gray regime is also where we test. And so we can actually see that the optimal velocity result is closely tracked for these out of distribution traffic densities as well, which is also often surprising in reinforcement learning. So I will just skip over this, but we can do this for a lot of other settings. The reason we talk about the single lane circular track is because it is very nice and simple, and we can actually reason about the optimality. But now when we look at, now we're interested in this sort of curse of dimensionality as we look at more and more complex systems. And a sort of motivation I like to give here is that no two cities are the same. And even if we look at two chunks of like road network that are smaller, they're also likely not the same. It's possible that not even any two road blocks are the same. And there are a lot of reasons that they could be different. And it's a combinatorial space. We in order for reinforcement learning to be useful for this domain, we feel very strongly that we must be able to generalize across these elements, across networks. So that's something that we're very interested in. Can transfer learning work in this domain? Can knowledge be transferred across these scenarios? So for instance, we might have some source task like this, like the circular track. Does it have anything to tell us about some target task, which looks very different? This can potentially help with sample efficiency in addition. So we might try to extract some knowledge and then transfer it, and then we can even continue training. But in the extreme case, which is what we've studied here, is zero-shot transfer, which is where there's no training afterwards. Okay, so yeah.
Sorry, we have about 2 to 3 minutes before we take the questions.
Okay, thank you. That's perfect. All right, so just what I was talking about before here, this is an example of zero-shot transfer between sort of this density range and these density ranges, because you can view these as different networks, but maybe that's not as exciting. So here we have another setting. This is modeling a highway network. And here we're doing some training on this bottleneck network. So you can see vehicles sort of accumulating here, which we don't like. So we're gonna do the same thing where we have a fraction of vehicles, 10%, and we would like to avoid this sort of jam up of the vehicles. And there's this interesting phenomenon that I don't have time to talk about, which is called a capacity drop. So as you jam more vehicles into the system, this is the inflow, the outflow should increase linearly and then flatten out. But actually there's a drop, so this is called a capacity drop, where the vehicles are contending so much that that the capacity is actually lower than this peak as you increase the number of vehicles going in. So that's something that we're trying to avoid here by using by introducing autonomous vehicles, and we actually show that we can. Okay, so we trained this just like we did before, but now we're interested, can we reuse this controller in a different network? And we do find that yes, we can actually directly transfer, zero-shot transfer to bottlenecks of different sizes and shapes and numbers of segments. We can transfer to different like fractions of autonomous vehicles. And then sort of the most exciting, this is still ongoing work, is we can transfer to networks that look very different. So here's a grid network, which is sort of our like target benchmark right now. So we can basically see that by training on basically a highway network, we can get a 26% improvement on a grid network without any kind of fine tuning. So so that's all I wanted to share with you. This is just the beginning. We're just scratching the surface. I would say that we've done a lot of work to really justify to ourselves, to convince ourselves that this is a domain that is that reinforcement learning can potentially help with, and that I hope will open up a lot of interesting empirical and theoretical questions, and really get into can we actually in a way do some sort of counterfactual reasoning for societal systems. And there are a lot of interesting questions in terms of scalability of multi-agent systems. How can we operationalize these questions for the future? and then how can we deal with the human elements in this work. So I will end with that, with thanks to my collaborators and sort of a conclusion slide.
Thanks, Cathy. This is really interesting problem space with lots of great potential. Now we have some time for questions. I'll open the floor for questions.
I have a question. You sort of hinted through the talk at this idea that, as you said, control theory and reinforcement learning can have this happy marriage. And that makes perfect sense. I wonder if you can elaborate a little bit on, clearly control theoretic methods have their strengths. What are these strengths, and why is reinforcement learning not immediately replacing these old methods? Of course, I know they can't, but I'm curious to hear it from you.
Mm-hmm. Yeah, so something I'd like to highlight here, I wasn't sure how to work this into the talk, is that, but it's questions that I get sometimes, is that like in these scenarios, I have the model, right? I think there's some confusion. We talk a lot about model-free or model-based methods. Here, I have a model. The model exists. It is a simulator, but I don't necessarily have the analytical form of the simulator. But all of the control methods they're really deeply utilizing the model. So these methods have this additional information that is a lot stronger. And so the reason it's not so far apart is because here I do admit I have a model. I just can't access it so directly. So if the control theoretic methods can directly access the model, even if it's a more simplified form than the model that I'm using, the simulator, which might have a lot of additional, if statements and a lot more complex distributional assumptions. The control theoretic methods may still be able to provide bounds through potentially even analytical or numerical analysis.
Cool. And we have a question from the audience. Cathy, can you see the question?
Oh.
It's in the Q&A tab.
Yes. Okay, this is really cool work. Can you talk a little bit about how the simulation environments were created? It seems like they are an essential part of the research. Even in the simple circular lane, the natural traffic backup seems pretty robust. Yes, creating the traffic and environments is an essential part of the research. And this is not something we expected, because it's really touched on in like reinforcement learning classes. It is like the design of the MDP is actually where most of the time is spent. What is the reward function? And that actually is discussed in some RL classes, but what we actually struggle the most with is, what is the state? So one example as we go to more complex settings is, how do you order your vehicles? Like, how do you, like when a vehicle sort of moves from one road to the next, the ordering changes in some way. So so the discussion of, what exactly is the MDP that we're studying is a lot of the time. And yes, we spent a lot of time, interfacing near commercial, so the most advanced open source traffic simulators with reinforcement learning libraries, so that we can actually create MDPs that model the problems that we are interested in. And then we have to start very simple as well. All right, next question. Are there research combining queuing theory and RL concepts similar to the combination of control theory and RL? I have to think so. I personally haven't looked too much in that direction, but I have to think so. Can the current problem be formulated as a basis of graph-based neural networks? Yes, I think so, and that's sort of the direction that we're exploring right now. But didn't have a chance to share that today.
Can I ask a question?
Sure.
I'm curious about this, the point that defining the state space was difficult. I can imagine it's difficult partially because you have to sort of decide, am I going to use like an egocentric view for an agent, or is there going to be some other view that it's going to have? So what was it that made the definition of the state so difficult? Like, was there not a natural view for the agent?
There can be. So so like one difficulty is that the agents are changing all the time as well. So vehicles are leaving and entering the system at all at the same time, or throughout the episode. There is an egocentric view when we look at a system where we're controlling multiple vehicles. Then it's not clear what the egocentric view is, because like we could view it as a multi-agent system and then everything is locally observed, but we're also very interested in the global optimum as a centralized controller. What do you do? And then how do you order the vehicles across the roads? Like even it like one thought exercise is, if you have 2 lanes of road and you have vehicles in 2 lanes, how do you order them? Do you order the vehicles in the first lane first, and then add some buffer of zeros if there aren't enough vehicles, and then have a second lane of vehicles? So honestly, when we started thinking about these questions, the graph neural networks were not as prominent. So now we're hoping that graph neural networks can help us resolve most of these questions. But graph neural networks have a lot of scaling issues when it comes to reinforcement learning, especially. And so I think that's sort of what we're pushing on now. Can we actually help scale graph neural networks in the context of reinforcement learning so that we can overcome some of these issues? Yeah, great question.
Yeah, fantastic. Thanks again, Cathy, for the great talk. And I think now it's time to move to the next one. The next talk is by Shai Manoa from Technion.